We have discussed charging by friction, where you have two oppositely charged objects as a result. We've talked about charging by contact, where whatever the charged object is, say it's negatively charged, when it makes contact with something else, the new object that's getting touched also becomes the same charge, becomes negatively charged. And we've discussed what happens when you charge by induction. You're going to create an oppositely charged object from whatever you're inducing with. So if you induce with a negative object, the object you're inducing becomes positively charged and vice versa. Now what I'd like to talk about is some of the dangers that go along with discharging an object. Now a charged object can become discharged, and you can see it as sparking, or when you don't see it, it makes direct contact with something that is linked to the ground. You may not actually see the spark because it's not jumping through air, it's just going directly through solid objects to the ground. Since opposite charges, the positives and the negatives, are attracted to each other, that negative charge can jump between objects. That's the sparking that you'll see. When all the excess charge has left that original object, we would say the object is discharged. We talked about that in other lessons. The greater the charge difference between those two objects, the greater the actual spark will be, the greater the discharge. So here we've got a few extra negatives and a slightly positive other object. So we have a few negatives jumping across. Here we've got a very negative object and a very positive. So the bigger the difference in the actual charges, the more electrons you'll see moving towards the positive object. So this would be a little spark, a small discharge, and this would be a very large spark or a large discharge. This is a scenario that you have most likely encountered in your life. If you've ever rubbed your socks or your shoes on a carpet and then walked up and touched a doorknob or touched somebody's nose, you can actually see the spark, you can see the discharge happening. When you rub your shoes on the carpet, you're actually charging by friction. The shoe started off with its rubber sole, which is an insulator. It started off as being positively charged, and so did the carpet. But as you were walking and began to rub, what happened was the negative charges from the carpet in that particular area have been stolen by the rubber, because the rubber is more electronegative than the fibers of the carpet. So your shoe becomes positively charged. But now, because it's an insulator, those charges can't go anywhere. They're stuck. This is static electricity. Where they can go, though, is to you. They can't jump down to the ground again, but they can go to your leg that's sticking right here. Your body is a great conductor. You're full of water and all sorts of other things that like to conduct electricity. So that excess charge from your shoes begins to spread out along your body surface. Your finger itself actually becomes negatively charged by contact with the charged shoe. So the shoe became charged because of friction, and you became charged because you touched the negatively charged shoe. So the negatively charged shoe has now made you negatively charged by contact. So when you go to touch the metal doorknob, all those extra electrons that have been spreading around your body and cannot escape back to the carpet because of the rubber insulator, those are going to discharge to the doorknob and produce a spark. And you can build up such a big charge if you rub your feet for long enough that you can see a giant spark. Shut off the lights, try this. It's quite neat. You can see a little piece of lightning come out of your finger if you haven't done that already. It's quite fun. Now, we can have the same kind of an idea happening up in the thunderclouds. The wind turbulence, all that blowing of the air. There's water, there's ice crystals, there's dust up there and other particles floating around, there's gases up there. All of those different particles rubbing against each other as the cloud spins and pushes and turns causes friction between all the parts. And because of that, you're going to end up with positively charged and negatively charged ions. Now, the top of the cloud tends to gather the positive charges, and the bottom of the cloud tends to become negatively charged. Those charges separate. The negative part of the cloud then is going to induce, that means force, a charge on the ground by pushing away the electrons in the top part of the ground. So these negatively charged bottom part of the cloud repels the electrons that belong in the neutral ground just temporarily, and it pushes them down. Here's the second picture here. It pushes them down so that the top layer of the ground is actually left as slightly positive. Now, because I've got a negatively charged cloud near a very positively charged ground, as we have here, you're going to see the negative electrons jumping away from the cloud and diving down to the ground. And this is what you would see. This discharge that you would see is the lightning strike. The reason that lightning is so much greater of a spark than what you're doing with your shoe on the carpet is that there's just way more charges here. The difference in charge between the rolling cloud and the ground is much greater than between your rubber shoe and the carpet. When you are grounding an object, it literally means you've somehow connected that object to the earth through some kind of a conductor that is touching the earth. So you touch the conductor and the conductor touches the earth. The earth on the whole, this is very small earth, but the earth on the whole has an overall neutral charge. So in general, we'd say you have equal positive, negative. Now we can, for a moment in time, in a small area, maybe induce a charge, but as soon as the lightning jumps down, those extra electrons that jump from the clouds are just going to spread out and you're going to get a neutral ground again. So you can induce a temporary charge, very temporary charge, but that charge won't last for long because we have an infinite supply of electrons from other parts of the ground. And we have an infinite place to put the electrons that we may have pushed away or that we may have added from the lightning. So the Earth is this huge giant conductor, all overall going to have a neutral Earth. Like I said here, adding charges to the Earth is like pouring a cup of water into the ocean. The change is not noticeable and it does not damage the ground when you add those extra charges. Now, to avoid static charges building up near flammable materials like gasoline, we have a way that we can prevent the gasoline, which is sloshing around in a truck, from actually building up a charge. What we do is we can attach a conductor to that object and ground it so that the charge that does build up can flow safely into the earth. And here's our first example here. If you have an oil or a gasoline truck, that fluid that is inside, all that gasoline or oil that is inside that big round truck is going to be sloshing back and forth, back and forth, back and forth, back and forth. Or when the gentleman or lady jumps out of the truck and they're trying to deliver the gas, then you're going to have the gas flowing through the hose, or even if you're filling up your own car, you're going to have gas flowing through the rubber hose and you're going to get charging by friction. It's inevitable. You've got two different materials rubbing together. The fluid on the inside of the hose is rubbing. You're going to charge by friction. What you don't want is for the static to build up so that the charge difference becomes so large you produce a spark. But because the rubber tires are insulating the truck, while the truck is still moving, that fluid rubbing around the inside, there's no place, after I've charged by friction with those rubber tires, there's no place for that static charge to drop to the ground. So if somebody walks up and they're touching the ground and they touch the truck, a very large built-up charge is going to flow through them, causing a spark, and you really don't want a spark anywhere near oil or gasoline, anything flammable. And the next thing you know, you've got a fire on your hands, you've got an explosion on your hands. So what do they do? Because obviously we don't have oil and gas trucks blowing up all the time. Well, the solution is to attach a wire. Sometimes you've seen driving past cars or trucks, you've seen a metal chain dragging on the ground. Well, it wasn't because the guy had forgotten to, hook up his chain, although I'm sure that happens sometimes. But that piece of metal that is attaching the truck to the ground is doing it so that as the charges are happening, as you're getting the sloshing of the fluid against the container wall and it charges by friction, you don't build up a charge because any extra charge immediately goes to ground. If the charge can't build up, then there's no danger of a discharge. There'll be no spark, and you keep your gasoline truck and their driver safe. But obviously, we can't do that with an airplane. An airplane travels through air. There's a lot of different materials that are different from what the plane is made up. That's going to do some charging by friction. When the plane lands, the rubber tires are going to stop the plane from discharging as it lands, going to insulate that charge. And then that means that the first person that connects the airplane to the ground will discharge it, causing a spark. Well, airplanes are full of fuel. If that fuel ignites, kaboom. So how do you ground this the way that we did it with the truck? You can't attach a wire to an airplane and let it dangle all the way to the ground. That's just not feasible. So what can you do? Well, there's a special thing that happens called discharging at a point. Discharging at a point is when you have a piece of metal like this, and it becomes narrower towards the end. When the electrons begin to build up, because they're going to be stolen from the clouds and added to the metal wings of the airplane, as the electrons are stolen from the clouds and they build up on the outside of the metal frame of the airplane, you're going to have them come to a little point here, and when they get to this point, they're so close to one another that they push each other off, and they will actually repel each other, and they will jump off the end. And here's a real picture of what static wicks look like on airplanes. You may have seen these before and not realized what they're used for. So again, that's called discharging at a point. You've got the same problem with fuel being charged by friction, but we can discharge it while we're still in the air, as long as we have some kind of static wick where we can just discharge right away. So we pick up electrons. Let's say the plane is moving in this direction to the left. We pick up electrons, and then they flow off the end and they go back into the clouds where we stole them from. You never build up a charge, means you never discharge, which means the airplane is safe when it lands. You've probably noticed before, if you help with the laundry, that when the clothes are made of different material and they tumble together in the dryer, they get charged by friction. Sometimes you'll see a sock stuck to a t-shirt or something like that. Why does that happen? Well, again, it's the charging by friction. They're made of very, very different materials. So as they tumble and they rub together in the dryer, you're going to have some materials steal electrons and become negative, and then the other materials are going to lose their electrons and become positive. As soon as they are oppositely charged, they stick together. So your negative t-shirt is attached to your positive sock, or vice versa, whichever it is, depending on the materials. So how do you stop that? How do you prevent static from building up inside your dryer? Because nobody likes staticky clothes. Well, the solution is to throw in a fabric sheet or a dryer sheet. And basically what that does is, as the clothes are turning and they're flipping and tumbling together in the dryer, there's a bit of soap on these sheets, a very, very tiny bit of soap, little soapy film, and it rubs all of the material the same amount, so that as the t-shirt rubs against another t-shirt or rubs against a sock or whatever, really what you end up having is only the soapy film on the outside of all the clothing actually interacts. If it's soap on soap, well, that's the same material. It's not going to steal electrons from another bit of soap, so you get no charging by friction, which means you get no problem with a charge building up, no need to discharge. And finally, we come to the idea of lightning rods. Now, you know lightning rods are little pieces of metal that are attached to roofs to prevent the houses or the big buildings from being burnt when they get struck by lightning. But let me show you what's happening with them. The problem is that lightning will strike the highest point on the ground. So it'll, again, take the path of least resistance. So the higher something is away from the ground, the closer it is to the clouds, the more likely the discharge is to happen to that highest point. It's a very good reason to not be walking around in a soccer field when you are the tallest thing when there's a lightning storm, because you can get struck very easily by lightning. You don't even have to have the cloud overhead or to be raining in order to be struck by lightning. Lightning can travel quite far away, remarkably far away, miles ahead of where the actual storm is. So you need to be careful. As soon as you hear the rumble of thunder, you got to cancel the game. You got to get out of there, because you could get struck by lightning. Okay. Now, depending on what it strikes, it can start a fire. So let's say without the rod, you have energy from the lightning strikes the wooden frame of your house. Because wood is an insulator, electricity and heat do not conduct very well through it. That means the electricity moves very slowly, the electricity being the discharge from the lightning. It slows right down and has a chance to convert to heat. In that case, then, you now have a scorching of the wood, and you can start a fire because it's hot enough to start a fire. So that means your house burns down from a lightning strike. Not ideal. With a rod, on the other hand, here's what happens. As the cloud begins to induce a positive charge on the ground, so here's our cloud with our negative charges, and we're pushing the negative charges in the ground down. What happens is you've got the lightning rod attached to the top of the house, but also attached to a wire that connects to the ground. So you don't just have a metal rod sitting up there, you have a pathway for electrons to pass to the ground. Now you're going to have because of the negative charge here pushing electrons away, there's going to be just neutral particles floating around, little pieces of air and dust in the air and whatnot. What happens is, because the rod becomes positively charged by induction as these negative charges push the negatives away and into the ground, this positively charged rod can steal electrons from floating objects. And then those electrons are going to follow the path to ground as well. So then these positive objects floating around are going to be drawn up to the clouds, and they're actually going to cause a slight discharge in the area right around this rod. Well, if there's a discharge in this area, then the negatively charged cloud is less negatively charged. It's not going to have such a strong strike if it does go to ground. And if it does go to ground, it's probably not going to do it in this particular area because there's such a reduction in the charge difference between the negative cloud and the positive ground. Even if it did strike, because this is made of metal and it's attached to metal here, lightning will take the path of least resistance. So even if it strikes the rod, it'll travel safely down to the ground without ever heating up the wood that makes up the house. So regardless of whether it's stealing electrons and creating positive ions and floating them up to discharge the cloud, or whether it strikes and it takes it to the ground, a house with a rod or a building with a rod is much, much safer than one without. Let's say you were in a car and you struck a pole and the hydro line fell down onto your car. Why don't you get electrocuted while you're sitting in your car? Well, you are safe inside the car because there's a metal shell that conducts that current electricity away from you. You are only in danger if you try to get out of the car, and by touching the car and the ground at the same time as you step out, you would create a pathway for the electricity to pass to the ground through your body. You would be the grounding mechanism for that particular case. So if this ever does happen to you, stay in the car until help arrives. You need someone to take that electricity away from you, and then you are safe. The reason that your car doesn't burst into flame or get super hot or anything like that is that if it's current electricity touching your metal car and it conducts it away from you, there's no path to ground because of the rubber tires. But in the case of lightning, the rubber tires do not stop the car from discharging to the ground. If the lightning, which is static electricity, can jump a few miles from the sky to your car, then the foot down to the ground is not going to stop it. And that concludes this lesson.